Now, if you remember, we have been for some time discussing the vector potential. We did an example on Wednesday. We will continue 2 more examples on vector potential today. Do you have any questions before we continue, though? So basically, I would like to discuss the infinite line, the vector potential of an infinite line, and the vector potential of a rotating sphere. There is a solution of this rotation sphere in the book already. I would like to solve it in a different way. So let's start with an infinite current carrying wire. And we would like to find the vector potential, let's say, at this point A. And if you remember, the expression for the vector current was 1 over C J R prime, this volume integral. Well, it just looks like the scalar potential, the only difference being the charge density is replaced with the current density. Now, in this problem, let's just choose our axis x, y, and z. J, the vector current density, first of all, it's in the z direction. It is non-zero everywhere except that x and y is equal to 0. So there should be some Dirac delta x and Dirac delta y over there. Let's say it will be I times Dirac delta x, Dirac delta y. Well, to check it, let's just calculate the total current passing through the xy plane. I mean, the total current passing through the xy plane should be I, if we did it correctly. So I should be equal to JR dx dy in the z-hat direction. This is my ds in the xy plane. So if you just substitute the expression for the vector current, we have the I delta x delta y dx dy. And the x and the y integral, we can just evaluate them. They both range from -infinity to +infinity. So the integral just gives 1 using the Dirac delta, and hence it is correct. So the overall factor in the current density is also correct. Now let's substitute it in the expression for J. So you see that J only has the Z component, so the vector potential only has the Z component also. AZ is 1 over C. Well, in fact, we can just use this identity, I times dl divided by r minus r prime. Remember, J dv is I dl for a vector current, for a line charge. And you can always make this identification. The volume integral contains 3 integrals. If you have a line charge, you have 2 Dirac delta functions, basically restricting it to a line. And hence you can just carry out 2 of the integrals using your Dirac delta. What remains is I times an integral along the line. Well, just for simplicity, let's just assume that, we have translational invariance. So basically, this vector potential cannot depend on the z coordinate. It can depend on the x and the y coordinates only. So for simplicity, we can just assume that r is equal to x in the x hat plus y in the y hat. We can just look at a point on the xy plane. Because of translational symmetry, once we obtain that, everything will be translationally invariant. Well, in fact, it will even be, it will be a function of x squared plus y squared only, not x and y separately because of the rotational symmetry of the problem. Nothing changes if you rotate the system. But for the time being, let's stick with the Cartesian coordinates. Now, r prime is, let's say, z prime in the z direction. We are just having the current is along the z axis. So r minus r prime, the magnitude is nothing but x squared plus y squared plus z prime squared under the square root. dl is just dz prime. So if we just substitute everything back, az is equal to 1 over c, the integral I over c, the integral of dz prime over, let's say s squared plus z prime squared under the square root. Now let's just assume that we are integrating from minus L to L for the time being. Eventually we will take the limit L goes to infinity. So what is the result of this integral? Do you remember? Well, now let's make a change of let's make a change of variable. Z prime is equal to S tangent theta. dz prime will be S over cosine squared theta d theta. So AZ will be I over C. Let's ignore the limits for the time being. S over cosine squared theta. 1 over S 1 plus tangent squared theta to the power 1/2 d theta. Well, this factor 1 plus tangent squared theta is nothing but 1 over cosine theta with the square root. So it cancels one of these ones. S's cancel. So A of Z is equal to I over C d theta over cosine theta. Now what is this integral? Well, let's see. Jihad claims that this integral is equal to tangent squared theta. Let's check it. How do we check it? Just take the derivative. This is equal to twice tangent theta times the derivative of tangent theta, which is 1 over cosine squared theta, which is not equal to 1 over cosine theta. So it's not tangent squared theta. Well, if you do not remember integrals, you can just try to derive them. How can we try to evaluate this integral? Okay.
Then cosine squared theta is 1 minus sine squared theta. Sine squared theta would be sine theta is u. There's the function of the numerator. Can you get something?
Well, your claim is, let's just say AZ is equal to I over C cosine theta. Now cosine theta d theta divided by 1 minus sine squared theta, which is equal to I over C integral of d by d theta of logarithm of 1 minus sine squared theta. Well, if you take the derivative of this logarithm,
I didn't claim results. Use substitution, sine theta is u, and the result I don't know how to calculate.
well, let's see, sine theta is u. So this is du over 1 minus u squared. This is equal to I over C, 1 over 1 minus u plus 1 over 1 plus u divided by 1 over 2 du. This is equal to I over C times 1 over 2 logarithm of 1 plus u divided by 1 minus u. This is the indefinite integral. Let's just go back and do our substitutions. U is equal to sine theta. This is our theta. U is equal to sine theta. So this is, if you just call the hypotenuse 1, this is what we have the U. And so tangent theta is equal to U over square root of 1 minus U squared. And Z prime is equal to S. Sorry, what I'm trying to do. Yeah, S is known. Yep, sorry. Now what we are trying to do is express U here in terms of Z prime. And at the same time, if this is u over here, so you see tangent theta is equal to z prime over s. So this is z prime, this is s. Here we have 1 minus u squared. This is z prime squared, no, this is theta, plus s squared. So u is equal to z prime over z prime squared plus s squared. So az is equal to I over c 1 over 2 logarithm of 1 plus z prime over square root of z prime squared plus s squared divided by 1 minus z prime over square root of z prime squared plus s squared, and z prime goes from minus L to L. Or I over c 2c logarithm of square root of z prime squared plus s squared plus z prime divided by square root of z prime squared plus s squared minus z prime. Z prime goes from minus L to L, and the result would be I over c logarithm of z prime's L squared plus s squared plus L squared divided by, plus L divided by L squared plus S squared minus L. Now, let's repeat what we did. So we had this integral. We first made this change of variable. Z prime is equal to S tangent theta, so that here inside the square root, we would get 1 plus tangent squared theta square root, which is, we can just evaluate explicitly. So 1 plus tangent squared theta is 1 over cosine theta, and we reduced our problem to this expression, where theta and our original integration variable Z prime is related by this. Then we made another change of variables, as your friend suggested. We just multiply the numerator and denominator by cosine theta, and sine theta is equal to u. And the final integral we obtained was simpler to evaluate. We obtained this 1 over 1 minus u squared factor, which we wrote as the sum of two terms, 1 over 1 minus u plus 1 over 1 plus u. When you just equate the denominators, you get 1 minus u squared in the denominator, the u's in the numerator, they cancel, but we have a additional factor of 2, so 2's cancel. That's why I divided by 2. Well, this integral is now trivial to evaluate. They are just the logarithms. The first one is the minus the logarithm of 1 minus u. The second one is plus the logarithm of 1 plus u. So I just wrote them as the logarithm of 1 plus u over 1 minus u. Now, the next thing is to relate this u to z. Remember how we defined theta first. This is our theta angle. Tangent theta is just z prime over s. So here, this is z prime. Here we have s. So this is z prime squared plus s squared. So u, which is sine theta, which is just z prime over the square root. And then, yes. Well, you see, the integral of 1 over 1 minus u du is minus the logarithm of 1 minus u. Because if you take the derivative of logarithm of 1 minus u, you get 1 over 1 minus u, but you also get the derivative of 1 minus u, which is minus 1. This is the vector potential. I over C, the logarithm of square root of L squared plus S squared plus L over square root of L squared plus S squared minus L in the Z direction. Now, okay, this is just the contribution to the vector potential by a segment of our wire of length 2L. If we want to get the total vector potential, we have to sum all of them up. So we have to take the limit L goes to infinity. But you see, if L goes to infinity, the numerator becomes infinite. The denominator, well, I think it's fine. It goes to 0 or some finite number. So it goes to 0. It's infinite minus infinite uncertainty. But if you just ignore the S squared, it goes to 0. So this is divergent. Well, we already know that this problem is kind of trivial, no? We know that it is, the magnetic field is just 1 over S. So how would you propose to solve this issue? We have this vector potential which diverges. By the way, did we have such a divergence in electrostatics? I mean, the analog problem in electrostatics was this infinite wire with uniform linear charge density. Did we have such a divergence there? Let me ask this question then. What we usually do is we just set the potential at infinity to 0. Yep. Because if we do set the potential at infinity to 0, then the potential diverges. But you see, this solution, we started with this one. This is the expression of our vector potential. Oops. This solution already assumes that the vector potential goes to 0 at infinity. So this is the origin of this problem is basically still the same. So we cannot really set the vector potential at infinity to 0. Now let's solve this issue. So let's see. Let's make an expansion. L, we will assume very large, and let's make an expansion of this factor in powers of 1 over L. And let's see what we will have. So we have this square root of L squared plus S squared, which is L times square root of 1 plus S squared over L squared, which is 1 L times 1 plus 1 over 2 S squared plus over L squared, plus other terms. Let's hope that this much will be enough. So then AZ, which is I over C times the logarithm. Well, the L's in the, let me just keep it. 2L plus 1 over 2L S squared, which is the numerator. You see, I have plus L in the numerator, so that's why I ended up having 2L plus the second term, divided by L times 1 over 2L times S squared. Now, in the numerator, I have this minus L. The minus L will just cancel the first term in my expansion, so I'm left with the second term only, which is I over C times logarithm of, let's see, 4L squared plus S squared divided by S squared. This is I over C times the logarithm of 4L squared times 1 plus S squared over 4L squared times 1 over S squared. Well, to be formally correct, let me introduce some other length scale in my problem. It's kind of arbitrary. L0 is just some other number, some other length. L0 is arbitrary. Well, in electrostatic case, it basically corresponds to, remember, we couldn't set the potential at infinity to 0, so we just set the potential at some finite distance from the wire to 0. Similarly, this L0 is related with where do you put the vector potential equal to 0. Well, usually let's look at the first term. The first term is the divergent part. When we set the L goes to infinity, it diverges. But it's a constant. So if you just change the vector potential by the gradient of a function, we already seen that the vector potential does not change. Well, a constant, you can always write it as the gradient of some function. So we can just get rid of it. Furthermore, the gauge, remember, we have a gauge condition also. The divergence of the vector potential is equal to 0. Unless we state otherwise, we are working in that gauge. Well, shifting the potential by a constant doesn't even change its divergence. It doesn't change its curl. It doesn't change its divergence. So we can just ignore it. It doesn't have any physical consequence. So A, corresponding to our infinite wire, ignoring this infinite piece, which we can write as I over C. Now, if we ignore the first piece, now I can take the limit L goes to infinity, because the remaining pieces are finite. I end up having the logarithm of L0 over S squared. Well, let me just call this L0 squared, sorry. L0 squared over S squared in the Z direction. This is the vector potential of my infinite wire. Well, you see, the derivation is kind of straightforward, except then the technical detail. The thing you have to pay attention to is use the Cartesian coordinates to evaluate the vector potential. Well, this problem has a peculiarity in the sense that since the current just extends to infinity, we cannot really set the current at the vector potential at infinity to 0. So what we do is we first take the contribution to the vector potential from a finite segment of the wire, a segment of length 2L, then calculate the vector potential, then it will be finite. When you take the L goes to infinity limit, when you sum up all the contributions from all the segments of the wire, you are free to just change the vector potential by a constant. In fact, you are free to change it by the gradient of any function. It will still give you the same magnetic field. And you can just ignore this divergent constant. Remember that, note that that constant doesn't depend on S. That is crucial. So I can just ignore them. The curl, it won't affect the curl. And in the remaining part, it is finite in the limit as L goes to infinity. For an infinite wire, the remaining part I can identify as one of my vector potentials. Remember, the vector potential is not unique. There are infinitely many vector potentials corresponding to exactly the same magnetic field. If you shift your vector potential by the gradient of any function, you still get the same magnetic field. Now, as a second example, let's look at the rotating sphere. Rotating spherical surface charge density. So what we will assume is that we have this sphere of radius r. It has the surface charge density sigma, and it is rotating around this axis with an angular velocity omega. Now, this time we will have not a volume current density, but a surface current density. If you remember, the volume current density was the current running per unit area. The surface current density is the current running per unit length. So you see the charges are moving in this direction. That is the motion of the velocity of the charges. And so if you just take this such a length over here of length dl, there will be a current di running through it. And let's say the surface current density will be nothing but di over dl. Or another way of looking at this, we can just say that we can go ahead and write the J, but J will be basically K multiplied by a Dirac delta. So we can try to write the J first. Once we write the J, we will see that it is proportional to this Dirac delta, and that proportionality constant will be the surface charge density, surface current density. Now let's do it both ways. Remember, J is equal to rho times V. Rho, the volume current density at the point R is equal to the volume charge density at that point multiplied by the velocity of the charges at that point. Now, rho is nothing but sigma times Dirac delta R minus R. So here comes our Dirac delta. What is the velocity at that point? At this point? Well, let's see. Velocity is equal to omega over r. This is a claim. Or let's just look at the magnitudes. Let's look at the units. Well, that's the first thing you should check in your answer. The unit of omega over r. What is the unit of omega? 1 over second. What is the unit of r? Meters. So this is equal to 1 over meter seconds. So omega over r cannot be equal to the velocity of anything. So omega cross r, this is what you claim. Let's see if it will be correct. So the units will be fine. R is meter, omega is 1 over seconds, omega r has the correct unit. The velocity at the pole should be 0. Well, if you look at when r is at the poles, that's r is parallel to omega or anti-parallel to omega, so the velocity is 0. So it seems to work. Let's look at the velocity at the equator. The velocity at the equator should have a magnitude omega times r. And at the equator, v cross omega cross r, since omega and r, they are perpendicular to each other, it's omega cross r. So this is the let's look at the directions also. Do the directions match? Now at this point, the velocity is into the screen at r dl. Well, omega is upward. If you just take the cross product, it's into the screen. So the magnitudes match, the direction match, and hence the answer is correct. So J is equal to sigma omega cross r. This is equal to times Dirac delta, r minus r, and hence K, the surface charge density, is sigma omega cross r. Now let's look at the other way around. Let's just try to use this definition. Well, we can imagine this strip of radius this has a radius of, let's say this angle is theta, r sine theta. So the circumference of that strip is 2 pi r sine theta. What is the charge in that strip? That strip has a length dl. So has a thickness dl. So the area of that strip is 2 pi r sine theta times dl. This is the area. If we multiply it by sigma, this is the charge in that strip. All of this charge passes through that line segment dl in one full rotation. And one full rotation takes a time 2 pi over omega. So di, the current running through that dl, is just dq by dt, which is omega r sine theta sigma times dl. Or k is equal to di over dl, which is omega r sine theta times sigma, which is nothing but sigma times the magnitude of omega cross r. Well, if you just look at the direction of the k vector, it is also in the same direction as omega cross r. So k vector and the sigma times omega cross r vector, they have the same magnitude, same direction, so they have to be equal. So the vector potential will be 1 over c, well, if you want to, k times Dirac delta r minus the radius dv divided by r minus r prime. So no, this is r prime. Integral over dv prime. K at the point r prime. You can just try to evaluate. The derivation is in your book, so I will not repeat it. Let's just do another thing. So what we are interested in, we know the current density. We are interested in calculating eventually the magnetic field. Once we obtain the vector potential, we can take its curl and calculate the magnetic field. Now, the magnetic field satisfies these two equations. The divergence of B is equal to 0, and curl of B is equal to 4 pi over C times J. Now, let's assume we are either inside the sphere or outside the sphere, not on the sphere. So if we are not on the sphere, curl of B is equal to 0. And divergence of B is also equal to 0. They are both 0, just like in electrostatics. So we can define a scalar potential. We can write B as minus the gradient of some function, since its curl is 0. And since the divergence of B should also be 0, the Laplacian of this phi m should also be 0. So this is the scalar magnetic potential. You can write the scalar magnetic potential in a region where there are no currents. J is 0, curl of B will be 0, so B should be, you should be able to write B as the gradient of some function. Well, we had already, this is a spherical symmetric problem. We had already studied the spherical symmetric boundary value problems in electrostatics. We know the general solution. So both inside and outside phi m should have the form sum over L and m's, L m divided by R to the L, no, times R to the L plus B L m times 1 over R to the L plus 1 times Y L m of theta and phi. But you see, we have this rotational symmetry. Nothing changes if we rotate around Z. So the solution should be independent of phi. The phi coordinate. Well, we know that YLM depends on phi if m is non-zero. If you remember, the dependence of YLM on phi is e to the power im phi. So only the m equal to 0 terms can survive, can exist in this summation. Now, if that is the case, I only have a summation over L. So let me just give them some different names. A L R to the L plus capital B L over R to the L plus 1. YL zeros are nothing but Legendre polynomials. Now, there's a proportionality constant. Those proportionality constants, I just multiplied that with the small a's and b's to obtain the capital A's and b's.
I remember YL0, the sum over all m for single value for L gives the legendary polynomial.
No. You see, we have this one. Where the angles are, you see we have this R vector we have this r prime vector. Gamma is this angle over here. Oh, sorry, I'm not summing over L.
So it's the sum over M.
Sum over M. Yes, you're right.
So if I specify it will be 0, I
No.
can replace YLM by...
You see, this is one property of YLMs, and keep in mind that the angles on the left-hand side and the angle on the right-hand side, they are related, but they are not equal. But YLM itself, for one of them, is proportional to, with the normalization constants, PLM cosine theta, e to power I m phi. This is one of them. So when I set m is equal to 0, that exponential doesn't appear. E to power I 0 is just 1. And PL0, which are called, PLM, which are called associated Legendre polynomials, when you set m is equal to 0, you obtain the conventional Legendre polynomials. So that's what I'm using. These are different properties of the spherical harmonics. So now I have this general expression of my magnetic potential both inside my sphere and outside the sphere. Well, I will do, there are other restrictions. This potential should be finite everywhere. If inside the sphere, if I'm inside the sphere, r can take the distance from the origin can take the value 0. So if the potential is finite, then the second term should be 0, the BL term should be 0. So inside the sphere, phi m r should have this form. A L r to the L y, no, P L cosine theta. This is inside. Outside the sphere, well, at infinity, it should go to 0. My charge is localized over here. At infinity, there is nothing. This is not like the infinite wire case. The infinite wire just extends to infinity, but this doesn't extend to infinity. So at r goes to infinity, this should go to 0, but the AL terms, they don't go to 0. They either diverge or they remain constant. So the AL terms should not be there outside the sphere. So I only have the second term. Now I need to find some way to relate these A's and B's with each other and also with the current density on the surface of the sphere, on the boundary. So I have to now determine how should I match these two solutions on the boundary. And for that matching, I will use these conditions. Divergence of B should always be equal to 0, even on the boundary. And curl of B should be equal to 4 pi over C times J. Now, you see, whenever you see a divergence, you can think of a volume integral. So this tells me that across any surface, in fact, if I integrate B over any closed surface, this should be the integral of divergence of B over the volume inside that surface, but divergence of B is equal to 0, so this is equal to 0. Now, just like in electrostatics, remember what we had done in electrostatics, we had looked at an arbitrary surface. We chose such a cylinder and eventually took the limit as, let's say, this is D, this is also D, this is the area. Eventually we set the limit D goes to 0, and which told us that how the perpendicular component of the electric field changes across the surfaces. We said that it was proportional to the surface charge density. our argument will be exactly the same, but there are no surface magnetic charge density. So the vertical component of this B field should be continuous across my surface. B perpendicular inside should be equal to B perpendicular outside. So this is one condition I have. Now B perpendicular, remember B is equal to minus the gradient of phi m. In this case, I have a spherical boundary separating my two regions. So B perpendicular is nothing but minus the derivative of phi m with respect to r. The perpendicular component is the radial component. So these are my phi's. If I just take the radial derivatives with a minus sign, minus, well, let me copy these. So minus sum over L, A, L, L, R to the power L minus 1, PL of cosine theta. This should be equal to sum over L, L plus 1, B, L over R to the power L plus 2, PL of cosine theta. These are the derivatives on the boundary. Well, Legendre polynomials, we had said that they are complete, they are orthogonal. So if you have two sum over Legendre polynomials, and if they are equal, the coefficients on both sides of the same Legendre polynomial should be equal. Otherwise, the equality cannot hold for all values of theta. So this basically tells us that AL times L R to the power L plus 1 plus L plus 1 times BL divided by R to the power L plus 2, this should be equal to 0.
R to the power L minus.
Yes. So this is one relation between AL and BL which doesn't involve the current.
Minus.
Well, you see,
Coefficient of B is minus.
no. You see, if you look at this phi, the magnetic potential both inside and outside, the derivative inside the sphere doesn't involve a minus sign. The derivative outside the sphere has an extra minus sign. So that is why on the left-hand side here I have this minus sign, which comes from the BR is equal to minus the derivative with respect to R. But on the right-hand side there are two minus signs, hence there are no minus sign on the right-hand side. And in the last line I just put them all on one side. Now, this is one condition we obtained from the divergence of B. Now we have another equation. The curl of B is equal to 0, not 0. Now the curl of B is equal to 4 pi over C times J. Now, if you remember, in the case of electrostatics, the curl of J, curl of electric field was equal to 0, and to make use of that, we had assumed an arbitrary surface, and we considered the loop going around that one. And because why a loop? Well, this equation basically tells me that if you take any loop, if you integrate it around that loop, this is nothing but the curl of B integrated over the area bounded by the loop, but this is 4 pi over C J dot dA, but J dot dA integral over an area just gives me the total current in that passing through that area, or it is 4 pi over C times the current enclosed by the loop. Now let's look at this point, and at this point I will just take a surface perpendicular to the current. The current, I will assume that at this point is, let's say, into the screen, the current density. And I will choose my loop to be in this direction, so that the total current running through my area bounded by the loop is positive. Again, I will just assume this is H, the other half is H. The surface just goes through the middle of my area. Let's say this is L, this is my L, this is my L. Let's just give some names, A, B, C, and D. So let's see, B dot DL. We can just split it into contributions from each one of those segments, but I will eventually take the limit H goes to 0, so there won't be any contribution from the segment crossing my area. So this integral will be just from A to B of B dot DL plus from from B to A. That is the direction that I chose for my loop. And then from D to C of B dot DL. Now let me define some vectors. This will be again my normal vector. Let me call this vector the M vector. M unit vector will be just the vector in the direction of N cross J hat. Again, J hat is the unit vector in the direction of J. So if you just calculate N cross J hat, you obtain N is perpendicular to the area. So if you take the cross product of N with any other vector, you get a vector that is tangent to the area. That's basically my M vector is. Now from B to A, my DL is basically in the direction of M. So this will be equal to L times B inside dot M. From D to C, my DL vector is in the minus M direction, and I'm outside my surface. Well, the inside and outside are defined by my choice of the normal vector. Remember, the choice of the normal vector defines what you mean by the inside and what you mean by the outside. N vector points from inside to outside. Plus L times B outside dot minus M. And this should be equal to 4 pi over C times the total current enclosed by my loop. But the total current enclosed by my loop is nothing but, no, this is the surface current density. It's just K, the magnitude of K times L. I already chose my area such that it is in the same direction. It's perpendicular to the current, or the area vector is in the same direction as my K. So that's why when I calculate the total current, there are no cosines or etc. due to the scalar product. Well, this tells me I can cancel the L's. So B inside minus B outside dot product with M should be equal to 4 pi over C times K. Now, I could have done exactly the same derivation by choosing a loop in the direction of J, not perpendicular to J, but in the same. Now I can. This is my J. Now I chose an area like this. This is my area, and it led me to obtain this conclusion about the component of the jump in the component of the magnetic field in this direction. I could have done exactly the same thing by aligning my loop in the direction of J. But in this case, the current running through this area is 0. So the direction of B in this direction, the jump in B in this direction would be 0. So this is the only jump in B. Only the component of B in the direction of M makes a jump. In any other direction, it doesn't change. So this is true for any surface current, not necessarily our rotating sphere. So let's go back to our problem of the rotating sphere. Now the direction perpendicular to the direction of the current is basically the theta hat direction, which should be discontinuous. Well, in fact, if we looked at the phi hat component, it is 0 both inside and both outside, so the phi hat component is continuous, as it should be. It's just the theta hat component that should be discontinuous, and be inside minus B outside. Let's see what is my theta hat component. You see, this is my direction of K. My n vector is this one. N cross K is M is equal to N cross K hat. It is towards the pole, theta is equal to 0. But that is minus theta hat. So this B inside minus B outside, take the scalar product with minus theta hat. This should be equal to 4 pi over C times K at that point. Or the theta component of B outside minus the theta component of B inside should be equal to 4 pi over C times K. We already know the theta component. You see the B theta would be minus 1 over R del over del theta phi M. So just take the derivative with respect to theta. Well, let's see. We have the expressions of phi inside and phi outside over here. So B theta, this is inside, is equal to minus L minus 1, because I'm dividing by R. I'm evaluating it at the boundary, and times the derivative of this PL. Now, B theta outside would be minus sum over L, BL over R to the power L plus 2, d by d theta, PL of cosine theta. So if you just take the difference, you get sum over L, A L R to the power L minus 1 minus BL over R to the power L plus 2 times d by d theta of PL of cosine theta. This should be equal to 4 pi over C times K, the magnitude of K. But we had already evaluated the magnitude of K is nothing but sigma omega times R times sine theta, which is 4 pi over C times sigma omega R, let me put a minus sign, d by d theta of cosine theta, which is minus 4 pi over C times sigma omega R d by d theta of P1 of cosine theta. Well, again, PLs are orthogonal. They're complete. Their derivatives will be orthogonal, complete, etc. So their coefficients should be equal on both sides. AL r to the power L minus 1 minus BL over r to the power L plus 2 should be equal to 0 if L is not equal to 1. And AL r to the power L minus 1 minus A1, sorry, L is equal to 1. A1 minus B1 over R cubed should be equal to minus 4 pi over C sigma times omega times R. And this is my A1. Plus I have the previous conditions. This is true for both L is equal to 1 and L is equal to 0. Now L is equal to 1 and L is different than 1. So basically, if you just combine this last equation with the previous two, AL is equal to AL is equal to 0, BL is equal to 0 for all L different than 1. Only the L is equal to 1 term will survive. Just a side note, AL is equal to BL is equal to 0 is wrong. AL and BL, they cannot be equal. So that's why I just erased it. These things have units, and AL and BL have different units. So that's why AL cannot be equal to BL, even if both are 0. That's a 0 with units. So let's solve for what they are for L is equal to 1. On one hand, we have this condition. On the other hand, we have A1 plus 2B1 over R cubed. This is equal to 0, which tells me that A1 is equal to minus 2B1 over R cubed. If we just substitute it in the first line, we get minus 3B1 over R cubed is equal to minus 4 pi over C sigma omega R, or B1 is equal to 4 pi over C sigma omega R to the 4 over 3, or 4 pi over 3 omega R, no, 4 pi over 3 R cubed times sigma omega R over C. This is our B1. A1, just minus 2 over R cubed, this one. So this is minus 8 pi over 3C sigma omega R. Minus 8 pi over 3 sigma omega R over C. So now we have inside phi m is equal to, remember it's A1 R times P1 cosine theta. All the other terms vanish. So this is equal to minus 8 pi over 3 sigma omega R over C times R cosine theta, or phi m is equal to minus 8 pi over 3 sigma omega R over C times Z. So we can calculate B inside. B for R smaller than capital R is just the gradient of this one. This is equal to minus the gradient of that one, 8 pi over c, 3 sigma omega r over c in the z direction. A uniform magnetic field inside. Now we can calculate the magnetic field outside. Phi m is equal to B1 divided by r squared times P1 of cosine theta. Now we already obtained B1. Nope, where's B1? Yes, here. This is equal to, this is B1 times 1 over r squared cosine theta. Let me just rewrite it in this form. Why did I wrote it like this? Basically, this expression is what we obtained also in electrostatics. If you remember the electric field of a dipole, an electric dipole, the potential, we could write it in this form. And then we could just take the gradient, obtain the electric field. The electric field, or in this case it will be the magnetic field, will be just mu dot r hat. No, I think it's the other way around. 3 mu minus mu dot r hat times r hat over r cubed. So this system basically acts like an electric dipole. And in fact, it's a magnetic dipole. If you remember our first discussion of the magnetic fields, we said that, well, the magnets behave like a magnetic dipole. And let's assume the form is also exactly the same. This is an example of a magnetic dipole. You have a charged sphere. It contains charge only on the surface, and it's rotating. Of course, you can generalize this problem to you have a sphere which has a uniform volume charge density, for example, and then you can go ahead and calculate the corresponding magnetic field. And it will still be a dipole. And if you would go ahead and calculate the corresponding vector potential, it will turn out to be mu cross r. Well, you had also your homework for today, by the way. Okay, even if I don't upload this as a separate homework as a PDF, this is your homework still. So you have this, just prove that this vector potential creates this magnetic field.
What's the point? Just take the curve.
Yeah, do some practice calculating. You need to practice a bit your calculations. Well, then we will discuss how do you define the magnetic dipole moment for an arbitrary current distribution. Then I will ask you to show that this magnetic dipole moment is actually this one. Well, just note one thing. Okay, phi m at an arbitrary point r. We had calculated for a point inside the sphere, and it turned out to have this form. And outside, it had this form. So we have these two forms. Is it continuous on the boundary? You see, in electrostatics, we always said that the potential is continuous. In this case, the potential is not continuous. You see, the continuity of the potential is the same thing as saying that the parallel component of our field is continuous, parallel to the surface. But in this case, the parallel component of the magnetic field is not continuous across a boundary if there are surface currents. So the corresponding magnetic potential is also not continuous. So the perpendicular component is continuous, the horizontal component, there is a jump. And those are your conditions to determine what the magnetic scalar potential is in this problem. And keep in mind that this potential we cannot define on the boundary, because on the boundary the curl is non-zero. But let's look at the magnetic field on the boundary. Well, it won't be continuous anyway. So there's no point in talking about the magnetic field on the boundary. Now, shall we give a 5-minute break?